Hello, friends. Welcome to Science Talk. I'm your host, Jim Massa, your resident oceanographer and climatologist. So I want to discuss with you what we see here. Now, I tried to record this video using the scrolling through the actual website, and this appeared on the webpage livescience.com. So if you were to go to livescience.com and type in Hothouse Earth into the search bar, this article should appear. Don't know what's going on, but I just kept running into problems with my computer locking up or having a black screen or just totally interfering with the program that I use to record my videos, especially when I'm doing screen, sharing the screen with you guys. So after about 4 attempts of this and several hours of basically not being able to record the video, I said, well, the definition of insanity is keep doing the same thing over and over and expecting different results. So I decided not to go insane, and I bagged it for last night, and I then took the verbiage of the article, turned into this document. So what I want to do is I want to go through this document here, and then there's an extremely important graph that I want to share with you, and I have that pulled up, and I actually have it in a much larger, I would say more visible, easy to see format than what appeared on the web page. Be that as it may. What's important is this right here. Earth is barreling toward hothouse state not seen in 50 million years, epic new climate record shows. Okay, 50 million years. That takes us back to the Eocene. And some of you may know about the Paleocene, Eocene thermal maximum, where during that period, about 50 to 53, 55 million years ago or so, Earth experienced its hottest temperatures ever. I just did a recent paper called Lessons from the Early Eocene, recent video called Lessons from the Early Eocene. And in this video that I made just a little while ago, go check it out, I shared with you some results that some researchers did. What the researchers did was they looked at the past information, they looked at the current trends of CO2 and temperatures, and they basically put it into their models, and the results of their models say that things keep going as they are. CO2 levels will be in the vicinity of 900 to 1,000 or more parts per million, and temperatures will have increased 7 to 9 degrees Celsius above pre-industrial revolution levels. Very stark. When you look at the models that have been developed thus far, up until a few years ago, they were basically projecting 3, maybe 4 C by 2100. Now those are turning out to be lowball estimates. Why? Most of the models assumed a linear increase. Now realizing as positive feedback loops take hold, they start jacking things up even more so. Basically, increases are now exponential, not so much linear. So now 7 to 9 C by 2100 is now a reasonable estimation, which is, of course, is very alarming. You got all these positive feedback loops kicking in. So you got the CO2, you've got the permafrost thawing, adding CO2, methane, nitrous oxide. You got the methane time bomb, all the clathrates and hydrates, and so on, especially from all the shelf area around the Arctic Ocean. You have that. And then as the oceans warm, and as they warm, Vertical sinking, which sequesters carbon dioxide and sequesters heat down to depth, that's slowing down. So that sequestration is not taking place at rates, at levels previously measured. And we have measured the slowdown of the vertical sinking in the North Atlantic, AMOC. So when you couple that all together, gas solubility in liquids decreases with an increase in temperature. So now you've got the surface water not sinking, so it's warming up. You're going to reach saturation, and at some point, you're going to outgas the CO2 back into the atmosphere. So that will all contribute to these rising CO2 levels. And when you look at the CO2 levels from the early Eocene era, they were considerably high. They were in the 4 digits, so basically 1,200, 1,400 ppms, quite high. So what this research did, and they did an excellent job of it. I went through the original paper and looked through it. It's lengthy, a lot of detailed analysis in there, and so I received a few comments of people asking me to include the precise links to these articles. I usually don't, for one very simple reason. To view these articles requires a subscription, and the subscriptions are not cheap. They're like $100 or so a year, and I'm sure a lot of people are not going to be forking out $100 here, $150 here for access to 1 or 2 articles, what have you. So that's why I don't usually give those links, but I do mention the source of it because I'm given the proper citation. Usually on some of the sites, you can at least see the abstract, but you can just go to the website and just put it into the search bar. So, but anyway, so these guys did a really excellent job with the analysis. And the problem with, we have very good data that shows the relationship between CO2 levels and temperature back to at least, like the last 3 million years or so. Very good data, very strong correlation. The further back in time that you go, the more error gets introduced in your sampling, in your measurements, because you're going, millions of years, tens of millions of years, hundreds of million years, the error is going to increase. So you have to then, and I've argued this in past videos, that you have to kind of look at those measurements with some healthy skepticism because of the large error that can be associated with it. So, but thanks to improved techniques, they're able to minimize the error. There's still going to be error, but they're able to minimize it and give us some really solid data that goes back 66 million years, basically right back to when that big rock came tumbling out of the sky and took care of the non-avian dinosaurs. Right? The record goes back to the dinosaur extinction. Well, the non-avian, because birds are dinosaurs. They survive. So a climate map showing the last 66 million years of Earth's history. Again, I will pull up this graphic at the end. I want to first go through the text here. The next 300 could be unlike anything we've ever seen. And Westerhold is the principal investigator, the lead author on this study, and that's the organization. 66 million years ago, right, the big old asteroid came down and basically threw a whole bunch of shit up in the atmosphere, ash, dust, rocks, blocking out the sun. And, blocking out the sun, there goes photosynthesis, there goes your food chain, food web, and you have mass loads of extinction. And that's basically what happened. One group that did okay were a group of amoeba called foraminifera. We just call them forams for short. They survived, especially the ones in the ocean. And forams make a shell, we call it a test, but they make a shell that surrounds them. But in the process of making their shells, they are basically recording conditions in the ocean at the time they made their shells. In other words, they're going to incorporate various elements. If they're making a shell out of calcareous material, calcium carbonate, so you got calcium, you got carbon, you got oxygen. You're going to incorporate the isotopes that made the shells. If you're making a shell out of silicates, you have silica and oxygen. So we can use the relationship of the isotopic ratios to reconstruct past climates. And I'll have more to say of that in a moment. So basically, the form they're reproducing, and so on. And then as they died, the shells sink, they get compacted into the sediment, and the information is locked away with it. So scientists have been studying these shells for decades, finding clues about ancient Earth's ocean temperature, carbon budget, composition of minerals going through air and seas. Okay? So this paper that was published in Science recently, September 10th, they've analyzed the chemical elements in 1,004 amp samples to build the most detailed climate record of Earth ever, and it indicates just how dangerous, dire, precarious, whatever word you want to use, the current situation is for humans. The new paper comprises decades of deep ocean drilling missions into a single record. So they collated, combined, pulled it all in, but put it together. Monumental piece of work here. We need to appreciate just the tremendous effort from this research team that went into constructing this record for us. And that details Earth's climate swings over the entire Cenozoic era, 66 million years since when the big rock came tumbling down, right through the current Anthropocene region, where Anthropocene, human causing changes to the planet. The results show how Earth transitioned through 4 distinct climate states called the warm house, hot house, cool house, ice house states. Ice house states being the most recent. In response to changes in the planet's orbit, I'll mention about that in a bit, greenhouse gas levels, and the extent of polar ice sheets. The zigzagging chart, again, I'll pull that up at the end, ends with basically what the article says, sobering peak, but in essence, we got a spike. And that spike is the addition of greenhouse gases caused by human activities. According to the researchers, the current pace of anthropogenic global warming far exceeds the natural climate fluctuation seen at any other point in the Cenozoic era, has the potential to hyperdrive our planet out of a long ice house phase into a searing hothouse state. Let me repeat this first part here. The current pace, right here, the current pace of anthropogenic global warming far exceeds the natural climate fluctuations at any other point in the Cenozoic era. Right there. The pace. I have stressed in my videos time and time again the importance of the rate of change. The rate of change, the amount of greenhouse gases we are contributing to the atmosphere and how it warms up the planet is far greater than 66 million years of records now indicate. So if any climate denier wants to, basically say it's all, no such thing as human caused climate change, whatever, you can basically say, stop it, dude. It's the rate of change. We have 66 million years of data that tells us otherwise. Okay? Far exceed the natural climate fluctuations. So Dr. James Zackos, who's professor of Earth Planetary Science, University of California, Santa Cruz, a co-author, says now that we have succeeded in capturing the natural climate variability, we can see that the projected anthropogenic warming will be much greater than that. That's very alarming. The IPCC projections for 2300, if we keep doing as we do, probably won't be humans by that point, if we keep doing what we're doing, will potentially bring global temperatures to a level the planet has not seen in 50 million years. Now, the IPCC, and for those who have watched my videos, you know that I've been rather critical of them. I haven't had to deal with them. They tend to underestimate everything and a lot of things. Hell, they even leave out methane in their damn reports. It's like, well, what's the bloody point? But this same 2300, the planet's going to increase by about some 14 degrees C, which is about what the current best estimates how much hotter things were in the PETM region time frame than current levels, about 14 degrees C warmer. There's some modeling. I already indicated the one to you, 7 to 9 by 2100. Well, you can probably reach that 14 C by 2200, a little earlier. So, to compile the new era-long climate map, the study authors examined fossil foram shells in deep-sea sediment cores. Okay, so when you make a sediment core or an ice core, the same idea. You have this big hollow cylinder, and typically they're about anywhere from 10 to 15 centimeters in diameter, typically. And what you do is you drill, has a cutting edge on the circular cutting edge, and you drill down into the sediment, into the ice, and you just extract however long a length that you pull out. And usually they come out in segments of about several meters, but you put them together so that, and you lay them out on tables in the lab. And if it's an ice core, in a refrigerated place, obviously, but you just lay them out, end to end in the correct sequence, and you can get cores that are 10, 20 meters or so in length, and you've got a record. And you can say, using radio isotopic dating, you can say, okay, this layer is this many millions of years ago, and so on. And then you can, take a sample and measure what it is you're interested in. It could be oxygen, isotope ratios, carbon. You can be looking at what was the plankton composition like. So there are a number of things that you can take a look at. So, again, the forums, so I mentioned that before. The deeper the science, the bigger the seabed, the older the forums estimated. It makes sense. The ratios of carbon and oxygen isotopes in foram shells hold critical climate information. The ratio between the oxygen isotopes, oxygen 18 and 16, can reveal how warm the surrounding water was when a foram constructed its shell. The higher the ratio, the colder the water. The ratio between carbon 13 and 12 shows how much organic carbon was available for the microbes to metabolize. And basically, a higher ratio correlates with more greenhouse gases in the atmosphere. So, a word about this. Let me stop right here to explain some of this. I did a lengthy video on isotopic fractionation where I explained what it is, what the concept of it is. And I went and I took some data and I went through the data explaining how to look at that information, use it, draw the deductions from it as how it helps recreate what's happened in past climate, when there was an ice age, when there was deep water formation, a thermohaline circulation or not. I went through a whole bunch of those things. Please check out that video if you have not seen it. So basically what they're talking about is, it says a warmer, the colder the water, the higher the ratio. What they're measuring is O18 to O16. So why is that? Why is when that ratio is higher, the water is colder? Because the O16 version of the oxygen atom, the isotope, is more likely, because it's lighter, it will escape into the atmosphere. So now you take that atmosphere, right?
O16
form in there, it's going to precipitate as snow, compacts into ice, like sea levels go down. But what does that do is it leaves behind more of the O18. So when you look at the ratio of O18 to O16, the ratio of O18 to 16 is higher, but the 18 ratio is higher relative to the 16. Keep in mind, these ratios are in terms of relative to each other. Usually the O18, number of O18 atoms does not change because it's too heavy to go into the atmosphere. So you're having less O16 in the water, more on the land in the form of ice and snow. And we see this when we look at the ratio of O18 to O16 in a 4-amp shell, we see it's higher. But then when you look at the same time period, when you look at the ratio of O18, O16 in the ice core, it's far less. More because relative to each other, it's higher in the water, but lower in the ice. Then when that ice melts, you have all that water melting in, pouring into the ocean, bringing lots of O16. It dilutes the concentration of 18 to 16, relatively speaking. So now it's the same number of 18, but now you've increased the number of 16 so that the ratio of 18 to 16 goes down. That's basically the general concept of it. Now, I have I explained that in more detail in that video. I also did an addendum video, quick little like 5-minute thing to explain how this the relative ratio. 1,000 O16 atoms, and I have 100 O18 atoms. Well, the ratio of 18 to 16 be 100 over 1,000. Okay, you can do the fraction reduction. But now let's say I remove 200 of those O16 atoms. I stick them in ice on the land. I still have the 100 O18 atoms. So now it's 100 to 800. So you see, because I've done what? I've reduced the denominator, making for a larger number. And then if I pour it back in, those 200, and then add an additional, say, 500 more O16 atoms, it's now 100 to 1,500. Increase the denominator, make for a smaller number. In all my cases, numerator stays the same. That's kind of an idea there. That's why I say it's relative to what the other's doing. And now for C13 and 12, a higher ratio correlates with more greenhouse gases. In other words, if my C13 to 12 ratio is up, that means there was more greenhouse gases in the atmosphere. If it goes down, there's less. And it has to do with the stomata of the plants, which are the little pores on the inside of the leaves. When they open and they pull in the greenhouse gases, if you have more greenhouse gases in there, the likelihood of encountering more of the C13 isotope is increased. Basically what happens. That's just a quick overview to give you the general concept of what isotopic fractionation is all about. It's an extremely important, invaluable tool that we use to analyze matters and reconstruct past climate situations. And we can thank Wally Broker for developing the technique. Because the team's climate record covers such an incredibly long time period, the researchers also had to consider astronomic impacts on the planet's climate. That is how Earth's slowly changing orbit and tilt toward the sun impact the amount of sunlight reaching different parts of the planet at different times, known as the Milankovitch cycles. Let me pause there again. I did, you guessed it, another lengthy video discussing the Milankovitch cycles. What are the Milankovitch cycles? There are 3 major forcings of the Earth's orbit around the sun. And these forcings impact, influence, and affect how the sunlight energy that comes into the planet, how that heat is distributed, and what it does to the planet. So what are those 3 major forcings? The first one is the eccentricity of the orbit itself. Now, eccentricity is a value that's calculated to assign how elliptical something is. The closer the value is to 0, the closer that shape is to being a circle. A circle, you might recall from your basic geometry, is really a special case of an ellipse. An ellipse has two foci. Focus is singular. The closer the foci get to each other, the less elliptical and more circular the shape is. When the two foci precisely overlap each other, you have a center and you have a circle, and the eccentricity will be 0. Now, the further apart the foci becomes, the more elliptical in shape. In other words, it's going to get drawn out this way and squished down that way. Right? Think of like any of the orbits of the objects that come into the solar system and go back out. Okay? So Earth's eccentricity ranges from nearly circular, but not exactly circular, to less nearly circular. So the range is not great, but it is significant. And that cycle is about of a 100,000 year duration, from going from nearly circular to its most elliptical and then back to nearly circular. That's about 100,000 years. The other aspect, another one, is the axial tilt, right? So think of this as the axis, and it tilts. Okay? This tilt goes back and forth like that, right? Like a wobbling top. And this tilt goes between like about 23 degrees or so to about 26 degrees or so. So it tilts to say as most tilted over 26, back to 23 and back to 26. That's about a 23,000 year cycle. Interestingly enough, when the Earth's axis is most tilted over, especially when whatever hemisphere is most directly pointed at the sun, because of the higher degree tilt, more solar energy, more insolation is received, and it's during those time periods when it's most tilted that, especially when looking at the ice ages, is when the planet's in the interglacial period. So when it straightens up a bit to a less tilt is when the planet, but not the only reason, tends to start sliding into an ice age situation. And finally, the third major aspect of the Milankovitch cycle is the precession of solstices and equinoxes. Basically, where they occur on the orbit, at what points on the orbit, kind of slides around. Look at my video to see the diagram so you can help you visualize it. But it slides around, and that, of course, will affect the energy coming in. So all these factors between, eccentricity. If the Earth is really elliptical and it's at apogee, you're not going to get a lot of sunlight energy, right? Well, if it's nearly circular, even at apogee, it's going to be closer to the sun, so you're going to get more energy. So you take all these things, the eccentricity, the tilt, right, the precession, right? They all combine to change the energy that comes in. Now, the precession cycle is about a 40,000 year cycle. So, let's say summer equinox occurs here. It slides around the orbit, and it will return back to that same spot there like 40,000 years later. So that's, again, a quick, nutshell kind of deal. So here's the important thing. When the team overlaid orbital data with the isotopic climate data, they saw that orbital variations created distinct but relatively small-scale changes to the global climate. Crucially, each big jump between climate states was tied to a massive shift in greenhouse gas levels. So if there was a sudden increase in temperature, it was due to an increase in greenhouse gases, and vice versa. A decrease in temperature, decrease in greenhouse gases. But the important thing is, when they looked at the isotopic data, when they looked at the orbital the data and the variation in the forcing, there was some changes to the climate, but they were small scale, because the forcing wasn't as great as it is now. And this is one of the things that is done in statistical analyses. Let's say you're investigating the response of a variable. That's your dependent, to whatever. That's your dependent variable. Well, there may be, say, 3 or 4 factors, independent variables, that will influence that response. So you have to look at those variables. You also look at any potential interactions between the variables, and then see how much each of those items contributes to the response seen. So if I've got a variable responding to 3 different independent factors, I can say independent variable 1 might have contributed, say, 17% to the response seen in the dependent variable. Variable number 2, maybe it contributed 31%. Variable number 3 maybe contributed 46%, right? And then you look at the interaction between 1 and 2. Well, that was not significant, but 2 and 3 contributed 2%. You get the idea. We can then say, looks like this variable was the most important one contributing to the response seen. And guess what? When we do that to what's going on with the climate, we see that human activity is, depending on which model you look at, is anywhere from 55 to 73%. But it's more than half. So definitely is human induced. In fact, the more and more recent papers I'm seeing, that number is moving up. So it's closer to like the 73 and 75% realm, which is very telling in of itself. So, for example, about 10 million years after the dinosaur extinction, Earth jumped from a warm house state to a hothouse state. That's that PETM I alluded to earlier, right? Paleocene, Eocene thermal maximum. So our temperatures up to 16 degrees Celsius above modern levels. Zackos said was driven by a massive release of carbon into the atmosphere, thought to be the result of huge volcanic eruptions in the North Atlantic. Similarly, as carbon dioxide disappeared from the atmosphere over the next 20 million years, ice sheets started to form in Antarctica and the planet entered a cool house state, with surface temperatures averaging about 4 C above modern levels. Okay. One thing I've noticed in a lot of papers looking at past climates is they don't seem to really be taken into account too much the position of the tectonic plates. I think they should be looking at that a little more so. Granted, in the last 66 million years or so, the positioning hasn't changed all that much, but it still has changed. When you look at, for example, going back to the Devonian era, most of the continents are like south of the equator in the southern hemisphere, but you had open polar waters there. So yeah, the planet's a lot warmer because you have open waters absorbing all that heat energy. You don't have ice forming. So now you got Antarctica. So Antarctica starts to slide south and south and south. So we're going to start getting snow, and the snow is going to build up, and it's going to form the ice. And then guess what ice does? It reflects sunlight energy back into space. So by the time Antarctica occupies its current position, you have all this ice, you have all that albedo, high albedo reflecting all that energy back into space. That cools the planet down. Couple that with the Arctic sea ice, right? You got these 2 big white masses at both poles. That's a lot of energy reflected back into space, which cools the planet down. Earth really started to cool down as Antarctica started moving south. Another factor was the Isthmus of Panama. When that rose, that blocked off a zonal circulation of the oceanic waters, which helps distribute heat based on, temperature, pressure gradients, and that kind of stuff. So now you're trapping, you're preventing the zonal flow, so you're getting more gyral flow, and that distributes heat differently. Because then it affects the atmospheric cells and so on. So now we know what we're doing to the Arctic sea ice. That's disappearing. So that's the reason why the Arctic's now warming 2-3 times faster than the rest of the planet. So you add these all together, and we're just cooking the planet. And we may be on course to what it was at the PETM. Only instead of being over the course of millions of years, hundreds of years. So about 3 million years ago, Earth entered an ice house phase. driven by waxing, waning ice sheets in the northern hemisphere. That's the ice ages, interglacials, that kind of stuff. This is where the Milankovitch, in fact, the Milankovitch was a Serbian scientist, and he proposed this hypothesis because he wanted to know why did Earth have ice ages and interglacials, and his hypothesis was changes in the Earth's orbit. This is 1920s he came up with this. Pretty remarkable. So now human greenhouse gas emissions, of course, are causing temperatures to rise to an extent not seen in tens of millions of years. This rise is well beyond the natural variations triggered by Earth's changing orbit. Right, I've got it highlighted there. This rise is well beyond the natural variations triggered by Earth's changing orbit. In other words, it is not Milankovitch. Recall the periodicity: 100,000 years, 23,000 years, 40,000 years. We're doing this in the hundreds of years, several orders of magnitude less. And if greenhouse emissions hold steady, the climate could skyrocket back to levels not seen since the PETM. The transition from Icehouse to Hothouse won't take millions of years. It will take hundreds. It's that rate of change concept. We know now more accurately when it was warmer or colder on the planet, have a better understanding of the underlying dynamics and the processes that drive them. And there's your lead author, Dr. Thomas Westerholt, director of the University of Bremen Center for Marine and Environmental Sciences in Germany. The time from 66 million to 34 million years ago, when the planet was significantly warmer than it is today, is of particular interest as it represents a parallel in the past to what future anthropogenic change could lead to. If you want to know where we might possibly be heading, learn from the past. Okay, so here's the URL, lifescience.com, and then types in the search bar Hothouse Earth, and just some memos to myself, some talking points. Now, let's look at this graph. Here we go. Okay. So what we have here is this is the graph that this research group constructed. Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, Holocene, and then the Anthropocene. And right here, this little bit, that's the Cretaceous. So this line right here, which if you follow it down, is about 66 million years ago. That's your KT event. That's the big rock tumbling out of the sky. And then exit stage left, non-avian dinosaurs. So as we can see here, okay, what do we have here on the vertical scale? The difference to the 61 to 1990 temperature. In other words, these comparisons, all these temperature comparisons, okay, is based on this 30-year average of global temperature. Okay? So in other words, it's not, if I look here at, say, 60 million years ago, it's not so much that the average planetary temperature was 12 degrees C. It's that it was 12 degrees C above this 30-year average. So this is our baseline. A couple of things here. On the scale here, for most part, it's in million years before present until we get to this white vertical line where there's a change in the scale. So instead of being millions of years, now KYR is thousands of years. This is kilo years, thousands of years before present. And then at about 1850, which is the start of the Industrial Revolution, they then break the scale down to smaller to go from 1850 to 2300. So as we can see here, this is warm house here and here. Okay. Hot house is right here. We see the darker red. This is your PETM, Paleocene, Eocene, thermal maxima. This is when Earth was at its hottest in the last 66 million years. Then it starts cooling down, possibly because after all that CO2 thrown up in the atmosphere from volcanoes popping off, the CO2 slowly got absorbed. Okay. Starts cooling down. And then this starts coinciding with Antarctica sliding southward. And we see that during most of the Oligocene and halfway into the Miocene, temperatures were pretty steady. So that's like So what's that? About a 20. So if I go here, that's 14 to say 34. Yeah, it's about 20 million year period. Things were pretty steady. Then it's still, so this is the cool how. Then it's still cooling down, getting colder, cooler, cold. Then it gets really cold. And here's where we get our ice ages, Icehouse ice ages, right here. Right. So we have the thick Antarctic ice sheets. We got the thick Arctic sea ice. Right. It's cold. Milankovitch is having conditions that foster ice sheet growth and low temperatures. Right. So it's really cold here. And as you can see, it's about -6 degrees Celsius below the 30-year baseline average. Then we're starting to come out of it due to Milankovitch. And then temperatures increasing. And then we hit the Industrial Revolution. And now, because this is relative, the scale, even though the horizontal scale changes, the vertical scale does not change until this little bit here. So it doesn't look like much, but if we were to blow up, expand the scale here, you would see a drastic increase. In fact, if you look right towards here, you can see it's starting to increase. And this is about to the present day. We have different models here showing the different, depending on what the models and assumptions are that they implemented. This line right here is that line that shows about 14 degrees C by 2100 or so. Let's see. So here's 20. This is about 2100. Yes, this is about here. Here's your 14C. That's about there. So these models are showing we're reaching nearly the 16C that we see up here. And now if you look at the graphs itself, see how it's kind of squiggly? That's Milankovitch. Right? Because this is a million-year gradation here. So 100,000 years is a tenth of that, and that would be something like right in here. So it looks a little blurred. That's because they got all the cycling going on. Again, if they were to expand it horizontally, really stretch it out, then you'll be able to pick out the little finer details of the Milankovitch forcing. But as stated here, while it affected climate, when we look at what we're doing, we're far exceeding even the climate forcing. So let's see, what else do I want to say about this here? You got the different models, and you got two models here. This one shows a slight decreasing. I think this model is assuming that humans' civilization doesn't exist, so things start leveling out. But this one here is showing 17 degrees, 18 degrees C, and probably 17 by 2300. That's incredible. That's crazy. Now, here's the other point. Even if humans were to disappear right now, there's enough thermal inertia, thermal energy in the system that warming will continue. You're still going to be thawing out the permafrost. You're still going to be, melting the sea ice, melting Antarctica, right? You're still going to be having all these things going on because all these positive feedback loops are in place. They've kicked in, which is why the increase we're seeing is exponential, not linear. So these are all still happening. And here's an extra wonderful aspect. There are thousands and thousands of wells around the planet where companies have drilled for methane. And that's for whatever reason, either they used up the methane, it was no longer economical, they closed operations down, and they capped off the wells. Those wells are leaking. A lot of them are leaking. They're leaking because, corrosion eats at the metal, and then the methane can leak through for whatever other reasons. But a lot of these capped wells are leaking. So even if humans were to disappear, human activity will still continue because we drilled for methane, and those caps are leaking, and it's putting methane into the atmosphere. There's an extra FU to the planet, right? So I said this is a really important graph. Hell, take a screenshot of it. But seriously, if you want to take a screenshot of this, save it to your folders, and just study it. You can see all sorts of interesting things here. Okay? You can see how it went from warm to hot to cool to ice, and we're coming back out into a cool house. So, and we're doing it on a much accelerated level than we've seen in the past. So, so there you have it. Human activities are driving the planet to a situation not seen in 53 million years or so. It's a situation that will result in human civilization coming to an end, to be quite blunt about it. Okay? You know, in addition to what we're doing to the planet, look at all the shit that's going on, right? We got the methane time bomb that could go off. We've got the warming Arctic. We've got the fires. We've got the crazier, more nasty storms. The stronger hurricanes. We've got affecting crop yield and crop nutrition. We just got all these things happening at once, and couple that with another contributing to this increase is that human population keeps growing. More and more people are going to require more and more energy. More and more energy means you're going to be extracting more and more fossil fuels, putting that into the atmosphere, further accelerating the increase. Right? And this one shows a correction here, probably because of pandemics, wars, starvation, lack of access to potable drinking water. This is all going to come down the pipe. I did a video talking about overpopulation. It's all going to come down the pipe. So you got all these things going on, okay? And if we go to 17 or 14, humans are gone. They're going to be off the planet. It's just because humans evolved in a cooler, low carbon situation, about 235 parts per million. We're at 416, 417. Let's keep it below 1.5 C warming. We're already at 1.3. We're going to blow past 1.5 before 2030. We'll probably hit 2, 3 C by, we'll probably hit 2 C by 2035, 3 C by 2050 if we keep going the way things are going. So, this keeps going. This will signal the end of human civilization, in my assessment. And the fact there was a paper I covered some time ago where a think tank out of Australia, a conservative one no less, basically said that at this rate, human civilization will cease by 2050. And along with the joys of the Arctic thawing, we don't know what pathogens are waiting to be released to nail our sorry asses. Just saying. So we're warming things up much, much faster at a much, 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 much higher rate than we have in the data for. And the way things are going, we might be recreating this situation here, only much faster, much sooner. Thank you for your time. I hope you found this informative. And again, please check out my Isotopic Fractionation, my Milankovitch, my lessons from the early Holocene, and population, overpopulation videos. Thank you again. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.